We're about to look at how to solve a limiting reactant problem using the BCA method. This BCA method is helpful when you have a complex limiting reactant problem, particularly when you want to find out the excess reactant that remains. So what a BCA problem is, the BCA stands for before, change, and after. And you're just going to make a table that incorporates the moles that you have of everything before, and then you'll have the change and after. So the first thing I'm going to do is rewrite this equation so it's a little bit bigger. All right. And then on this side, I'm going to write a B for before, C for change, and A for after. And underneath each chemical, I'm going to include the moles. So they're telling me I have 75.3 grams of copper 2 chloride, and I will trust that you all can convert from grams to moles. So if we do that, I'm using a molar mass of 134.45 for the copper 2 chloride. I have calculated the moles that I have before the reaction takes place to be 0.56. So I'm putting that here as before. And we have 106 grams of potassium iodide, and I'm also going to convert that into moles. And using a molar mass of 166, the moles of the potassium iodide before reaction is 0.638. Okay, now the products over here, we don't have any of them yet, so I'm putting 0. Okay, and now this is all moles, so I should put a little label to remind us that we have moles. Okay, so now think about this table as vertical math problems, and what's going to take place is the reaction is going to be shifting at the change. Okay, we're going to react it to go to the right, and what we're going to be doing is making some of these things that we said we had 0 of. Now the ratio at which we'll make them is dependent upon the stoichiometry. So it's the change that you'll be doing stoichiometry on. And let me highlight the change with red. Okay, so here. All right, so if we're thinking about making the copper 2 iodide, we're going to be making 2 of those, so I'm going to put a 2 times some amount, I'm going to call it X. Okay, and every time I make 2 of them, I'm only making 1 of the iodine. And the reason I'm saying 1 there is because of the stoichiometry. We see that there is a 1 in the coefficient there. So over here, if I'm looking at the potassium chloride product, the KCl, I see a 4 in front of it, and so the amount of KCl I'm going to make is 4, and of course X, because I don't know yet how much I'm going to make. Okay, so over on the right-hand side, I can see what I'm producing. And all of these X's are the same value, but of course we're making them at different amounts due to the stoichiometry, 2, 1, 4. Now, the reactants are going away, of course. So we're actually going to subtract those off when we change. And just like we did on the product side, we're going to use the coefficients. And so I will be losing the copper 2 chloride. This time, when I lose it, it's going to be a 2x. And the 2 again is coming from that coefficient right here, that 2. And then I'm going to lose the potassium iodide by 4x. All right. There. So my change And this is all based on stoichiometry, and by the way, the only place that you have to worry about these coefficients in a BCA problem is right there in red. The change part is where you use those coefficients. Now, everything turns out to be a little vertical math problem, and of course the ones on the right are the easiest, because if you look at it, on the right, the products, for example, the copper 2 iodide is going to be 0 plus 2x. So you're going to have 2x of that. So I'll just write that down. The iodide, if I vertically add, 0 plus 1x is 1x. And then KCl is going to be 0 plus 4x, so 4x. Okay, now things get more complicated on the left side. My vertical math problem is going to have that the copper 2 chloride, let's see, I'm going to have to write small here, is going to be 0.560 minus 2x. Okay. And then my potassium iodide is going to be 0.638, and I'm subtracting 4x. Okay. And now this row that I have an A next to is the after row. So these are all the things I'm going to have after. Well, if it's a limiting reactant problem, one of those two reactants has to be limiting, and I'm actually going to have 0 of it at the end. So either the copper 2 chloride after should be a 0, or the potassium iodide should be a 0. Now this is where we have to be a little bit clever, and we'll take an educated guess at which one is the limiting reactant. If I take a look at this, I'm going to go for the potassium iodide probably being my limiting reactant, because if I look at the original amount of potassium iodide, even though I have more moles of it, if I look at the mole ratio, I needed 4 moles of Ki for every 2 moles of the copper 2 chloride. So I actually needed twice as much, and if you look at the moles before, I'm looking at the 0.56 compared to the 0.638. If I compare those two, I clearly don't have twice as much Ki. So I'm going to guess, this is where I'm making an educated guess, guys. I'm just going to guess this one is my limiting reactant. All right. All right. So if I think that's my limiting reactant, what I'm actually claiming is that let's see if I can get a pen back, that 0.638 minus 4x is equal to 0. So 0.638 minus 4x, I'm supposing is going to be 0. Okay? In other words, this after it's all said and done, the amount of Ki will be 0. All right, well, if you look at this, I now have a pretty straightforward little algebra problem, 0.638 minus 4x equals 0, and I can solve that. When you solve that math problem, you are going to learn that x is equal to 0.160, and that's going to still be in moles. Okay? All right, now, back to remember the part about making the educated guess? I've done this for a few years, so I made a good educated guess. If you winding up with an x that gives you a negative number over here for one of these things, that means you chose poorly. Erase and you chose the wrong limiting reactant and go back and do the other one. For example, if someone had chosen in this problem for the copper 2 chloride to be limiting and set that equal to 0, they would have seen right away there's a problem with their math and start again. Okay, so I picked Ki, but again, I had an educated guess. If you pick the wrong limiting reactant, it's okay, you're just going to have to start over and figure out the other one is limiting. All right, so now I have what x is, and from here things get pretty easy. You're going to take that x and put it in everywhere. So, for example, my copper iodide, 2x, multiply 2 times 0.16, and you're going to learn that you have 0.32 moles of that. Things are getting kind of messy here. Try to put a box around it so you can see. Okay, there's my CUI. If I want to know my iodide, which is what one of the questions on this problem says, what mass of I2 forms, well, 1x. So I'm going to make 0.160 moles there, and I'll have to convert that into grams because they wanted mass. My KCl, 4 times 0.16. So 4 times 0.16 is 0.64 moles. All right. Now, the part that's really helpful about all this is over here on the left, the reactant, that excess reactant. Let's highlight the excess in green. This guy is excess. And this question is asking me how much excess remains. Well, now that I know what X is, I can sub it in, and that will tell me after the reaction's done how much excess I have. So I will do that. See if I can get more screen here. There we go. So we have already claimed over here on the left that 0.560 minus 2x. We said x was going to be 0.160. Okay, so I'm just using that equation. And when I solve, I learn 0.240 moles of the copper 2 chloride are in excess. The question wasn't very specific. It didn't tell me that I wanted it in grams. Certainly, if you wanted to, you could convert that into grams. So I'll do that quickly. Often they do ask you for grams. So just to wrap up the problem, 0.240 mole CuCl2, the molar mass, 134.45 grams per mole. So I would say you're going to expect 32.3 grams of copper 2 chloride in excess. Okay, the question also asks you for the grams of that iodide. So you could come back up to your iodide. We talked about it earlier. It is this, if I look under the iodide column, 0.16 moles I'm predicting as a theoretical amount. So because they asked for grams, I'll convert that to convert that to grams. Molar mass on that is 253.8. So our theoretical yield of the iodine is 40.6 grams I2. Okay, that represents the most we could make, remember. It might not happen in the lab, but that's the theoretical amount, the 40.6. What's nice about a BCA chart, if I just bring it back up here, is really any stoichiometry problem one could ask you about, you can answer now. You're going to be able to claim that Ki was limiting. There is nothing left after the reaction takes place. You could look at any one of the 3 products. In fact, if they asked you for all 3, simply take the moles that you've determined afterwards and convert to grams. And the most important part, which sometimes gets asked on a bonus question, is checking out that excess reactant, that one there that I highlighted in green. We were able to determine the excess amount, and then I went through and actually found the grams of excess that you could expect when the reaction was done. Hopefully that helps.